Okay, so hello everyone, we will be doing exercise 13.14 from the Pearson textbook. And so this question tells us that planet Z is 10,000 kilometers in diameter, and that the free fall acceleration equals 8.0 meters per second squared. And so the free fall acceleration is just a fancy way of saying gravity. So the gravity on planet Z is 8.0 meters per second squared. So we can just write out what we know so far. And actually, quickly, let's draw a diagram. And so if the diameter of the planet is 10,000 kilometers, the radius, which is the length from the center to the edge, would be 5,000 kilometers. And so let's write this in terms that we should use, which is using meters. As you can see, the acceleration is in meters here. So 5,000 kilometers is nothing but 5 times 10 to the 6th meters. So that is the radius of planet Z. And the gravity on planet Z is equal to 8.0 meters per second squared. And we also know that gravitational constant, which is useful for the formula we're going to be using later on, is equal to 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. And so the formula we're going to use today is that the gravity on a given planet is equal to the gravitational constant times the mass of the planet over the radius of the planet squared. And so this is going to be like our basic stuff we need to know for the entire question. And so part A tells us to find the mass of planet Z. And so we can use this given formula up here, right? And so we're solving for this variable, right? So we can rearrange the equation a bit. So we get mass of planet Z is equal to the gravity on planet Z times the radius of planet Z squared over the gravitational constant. And so if we plug in the given numbers that we have here, we will get that the mass of planet Z is equal to 8.0 meters per second squared times 5 times 10 to the 6th meters squared over the gravitational constant, which is 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. So we can see that the meters squared cancel out. So there's a meter here, meter squared there. That cancels out with the meters cubed. And since the second square is in the denominator on the top, and the second square is in the denominator on the bottom, they actually cancel out as well. And so we're left with kilograms, which will come to the top eventually. And so when we solve for this, the mass of planet Z is equal to 3 times 10 to the 24th kilograms. So this is our answer to part A. Part B tells us, let me move this up a bit. Part B tells us to find the value of free fall acceleration, which, as we discussed above, is just gravity at a height of 10,000 kilometers. And so what we know from the formula given above is that the radius here can actually be changed based on the height, right? And so what we would need to do is change this to accommodate for this 10,000 kilometers that we have right here, right? And so we can see that 10,000 kilometers is actually twice as much as the radius up here, right? So if we can probably, let me write this out in a clearer way. So 10,000 kilometers is 10 times 10 to the power of 6 meters, right? So this is the height above the North Pole. And so this is actually we can rewrite this as 5 times 10 to the 6th times 2, right? And so we've seen this 5 times 10 to the 6th before, which is up here as the radius, right? Which is 5 times 10 to the 6th. And so now we know that the height above the North Pole is nothing but 2 times radius of the planet. So now we can substitute this back into the equation above, where we add it onto the radius to give it to like make it seem like to find the acceleration at that height. And so what we would do, right, is we would find the gravity of planet Z, except now we should probably write a prime to denote that it's different from the actual gravity, and it's the gravity 10,000 kilometers above the North Pole. And so it's called G prime Z is equal to the gravitational constant times the mass of the planet, which is the same as above. But just now that the distance has changed, we're going to add it on to the radius. So the radius of planet Z plus 2 times the radius of planet Z, and then square that as we did above here. So basically, think of it as a way of changing the radius to account for this new height. And so we can just plug in what we know from up here again. And so we get 6.67 meters cubed per kilogram second squared times the mass of the planet, which we found in part A to be 3 times 10 to the 24th kilograms. And then do this all over the 3 times the radius of planet Z squared. And so this is equal to, so G prime Z is equal to 6.67. And so the kilograms here cancel out. And so we're left with meters cubed over second squared times 3 times 10 to the 24th over 9, since the 3 gets squared, 9 times the radius of planet Z, which is 5 times 10 to the 6th meters squared. And so if we solve this out, we actually get that the gravity at this height is equal to 0.89 meters per second squared. And so this is your solution to part B. So yeah, this is the overall work in case you guys need to like take a picture or something. And so yeah, thank you.